Today's going to be a great day because today we're going to be shifting and thinking about a new way to talk about juggling patterns, how to think about them, how to relate them, how to discover them. So where do we begin? Well, imagine that we're juggling. And what you can do is after a while you can be like, I'm just going to stop. And so we're like, Now, after you stop, you might say, wait, well, how does that help us? Well, what you do is you listen. And you say, okay, what do I hear? What you'll hear are the balls hitting the ground. And you might say, okay, great. I'll hear, if I'm juggling 3 balls, I'll hear 3 thuds, thud, thud, thud. But it's not just that you're hearing 3 thuds. It's how you hear the thuds. In other words, does it fall like boom, boom, boom in a nice regular beat? Or maybe it's boom, da, boom, pa, boom. Or it could be something boom, boom, pa, 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 boom. So in other words, what we're hearing is when we stop juggling, we see how long it takes for the balls to land. It's an indication of how far they are from landing. In other words, what's their future time that they're going to land. And so that's what we're going to be thinking about. How long does it take for the balls that are currently in the air to land? So that's going to be called a state. All right, very simple idea. So how do we use it? Well, first off, how do we record it? How do we write down a state? So there's lots of ways we could do it. One way we could do it is we could just say, okay, there's beats 3, 7, and 9 in the future is when they'll land. All right. But we're not going to do it quite that way. What we'll do instead is make a string. And it'll consist of zeros and ones. And what it'll be is each entry of the string is talking about a particular time. When will things land? All right, so great. Well, what do we mark? Well, 0 will be like nothing lands. And 1 will be something lands, right? So in particular, 0 in the ith position means, hey, I'm free currently, right? Things might change as time goes on. A 1 says, there's something coming in I beats. Be prepared. Now, one of the things that we're going to do is oftentimes we'll truncate it. What does that mean? Well, one of the things that we sort of have in the back of our mind is that when we think about juggling, we're under the sort of philosophy, hey, we've always been juggling, we'll always be juggling. Juggling is life. And, of course, the problem is that means that from a theoretical perspective, you could throw so that the ball might land millions or billions of beats in the future. Of course, in practice, it won't. Usually, we're pretty good if we can get away with 5 beats in the future. But what that means is if really we're keeping track of all the times in the future, we might have a state that looks something like this. 0, 1, 0, 1, 1, 0, 0, 0, 0, 0. And, well, what does this mean? Well, what's happening is it says, look, something's going to land 2 beats in the future, because that's in the 2nd slot, and 4 beats in the future, that's in the 4th slot, and 5 beats in the future, and nothing else. And so we don't want to have to keep writing down these infinitely many zeros, so what we'll do is instead, we'll say, hey, let's just truncate this, and we'll write this as 0, 1, 0, 1, 1, with the understanding that that's the last ball scheduled to land. In other words, everything else would be a 0 afterwards. All right, well, let's try this. Let's take a pattern, and let's talk about what's going on so that we can see what's happening. And in particular, we can say, here's a pattern. It's a period 4 pattern. In other words, it repeats every 4 beats. And what we'll do is we'll think about, all right, let's come and we'll reach a certain point and we'll stop. And we'll say, okay, well, what happened when we stopped? So, well, let's pick a point. So we can really pick any point. So suppose we said, we're going to stop after that point right there. Okay, well, what's happening? what we can do is we can see, look, there's 4 balls here, and each ball has its own color to help us. And we'll just see, where do the balls land that are currently in the air? So there's going to be a ball land there, and there's going to be a ball land there. And let's see. Oh, there's a red one. Oh, it's going to land there. And the yellow one, oh, that's way off away. It's going to land over there. And so there we go. 1, 1, 1, 0, 0, 1. And that's it. The rest are zeros. We don't need to write those down. All right, great. So that's if we were to stop right after we threw the 6. But we don't have to stop there. We can stop at other beats as well. So you can imagine, for instance, maybe we stop not here, but we were to stop at the next throw. All right, great. Well, let's see what happens there. So again, we say, let's take a look at the balls that are in the air. What happens to them? Well, we see the blue ball is about to come down. All right, and let's see what else. The green ball, oh, that's going to come down over there. The red ball is going to come down and into there. Good. And, well, what else haven't we done yet? Oh, we haven't done the yellow ball. That's still in the air. That's going to come down there. So there we go. 1, 1, 1, 0, 1. Now, of course, as you can probably guess, that's not the only place we can stop. We can stop somewhere else. So maybe at the next beat. What do we have? Okay, if we were to stop at the next beat, all right, so there's a red ball scheduled to land. Boom, right away. There's a green ball scheduled to land. Let's see. There's also the yellow ball. Great. Wonderful. And there's a blue ball. There we go. So that's actually really nice because that just says boom, 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 boom. All 4 balls are going to land in the next 4 beats. So they're really compact. See, as compared to what we saw before where they're stretched out a bit. All right. Well, let's try one more. Now, why one more? Well, why not? But actually, there's a reason for that. And let's move this up a little bit here so we can see it. And so if we go one more, what will we have? Well, there's the green ball still scheduled to land, the blue ball still scheduled to land, the yellow ball still scheduled to land, and the red ball. And there's that state. Now you might say, okay, what if we went and stopped at the next one? Here. Do you see what would happen? What would happen? Well, the thing is, it's a periodic pattern, which means if I just move everything over by 4, it's the same picture because it has period 4. And so in particular, if I move everything over by 4 beats, it's going to look identical to where we were. And so the moral of the story is it's going to go back to where we were. So in this case, it will start cycling around. So we really there's these 4 possible states that this pattern goes through. 1, 1, 1, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, and 1, 1, 1, 1. Again, we are allowed to repeat states. That's perfectly fine. Nothing wrong with that. And so in this pattern, we say, look, we're going to go from these 4 different states. And now, at this point, you're like, wow, great. This seems a lot more complicated, right? Before, we were just like, hey, here's like these 4 numbers, 6, 3, 3, 4. Now we're like, oh, look, here's these big strings which are somehow keeping track of all this information. But in essence, we really are storing a lot of information. You see, previously when we thought about site swap, it's a very localized, very what's happening right now phenomenon. Because that's the goal of site swap. I have a ball. What do I do with it? And I don't worry in general about what else is happening. Just say, what am I doing with this ball right now? And with states, we're like, hey, let's keep track of all this wonderful information that's available to us, and let's piece it all together. So it's going to be a slightly different thing, and we're going to see that actually we get a lot of beautiful information coming out of this. So when I like to think about states and what's going on, I actually like to sort of switch my perspective of juggling. And not so much focus on juggling diagrams, but to really think about juggling in a different way. And so I like to call this the conveyor belt model. And in other words, we're thinking about some sort of a conveyor belt happening where time marches on and the belt moves forward. And so let's actually talk about sort of a physical demonstration of this. And so I have something built out of Lego here. And what it is it really is just a conveyor belt. So let's put this down. Here we go. And we can turn the end, and lo and behold, things move. Now what's happening is things are moving forward. Now right now, there's nothing on this conveyor belt, but we'll put some things on. So here's how we should think of what's going on. Each beat here corresponds to our time step. Like this is 1 beat in the future, 2 beats, 3 beats, 4 beats, 5 beats, 6 beats, so forth and so on. And right now, there are no balls. So we'll put balls on, and we'll put them on by little pieces of Lego. Okay, so maybe there's something scheduled to land in 1 beat and in 3 beats. And, well, okay, here's 6 beats. All right. And we can even go to 8 beats. Why not? We can do it. Okay, so this is 4 balls. So what happens at each step? Well, in the conveyor belt model, we say, okay, we have our balls placed on the conveyor belt, and they're scheduled to come to the end of the belt. So here's the end of the belt at various times. So 1 time step, 2 time step, 3 steps, so forth and so on. So we move forward 1 time step. And what happens is as we move forward 1 time step, you see it pops out. All right, great. So now what happens? Well, we have to do something with this. You can imagine that what this really corresponds to is that a ball has come into my hand. And what I do is I'm going to throw it. So that means it's going to go so that it lands some number of beats in the future. In other words, I have to place it somewhere on the belt. Now, I can put it anywhere where I'm not currently occupied. So I couldn't have it land 2 beats in the future because there's already something here. Or I can't have it land 5 or 7. All those are occupied. But I could have it land 6. That's perfectly fine. And now, what happens? Well, you'll notice that what this says is that nothing's scheduled to land right away because there's an empty slot here. So as we go forward 1 step in time, nothing pops off. It's all the balls are currently there. How do we think of that? Well, that would be a 0 throw. Nothing happened. Okay, great. Well, now we go forward a time step again, and boom. Again, our ball landed in our hands. We've got to do something with this ball. What? Well, we can actually do a quick throw, a 1 throw. So it lands again on the next beat. And all right. And now we just keep continuing this. We move forward 1 beat in time, and we just see what happens. And this can keep going as long as you want. So that's how I like to think of what's happening with the states, right? Because the states are essentially saying, where are my occupied and unoccupied slots? So this would be read as 1, 1, 0, 1, 0, 1, and then the rest is 0. And of course, we can think of this as going on forever. In practice, if you're going to actually build this, you can't go forever, but you can go for a pretty substantial time. And so there we go. There we go. And this is fun. Well, maybe not as fun as real juggling, but there's also the advantage you don't have to be coordinated to actually experiment with things. Because, look, these are all things that you can do at your own pace. But one of the problems with juggling is it goes really quickly, right? And if you try to increase the number of balls, wow, forget it. Hopeless. But for the conveyor belt model, it's really easy for us to increase the number of balls. We just add more balls into the diagram. And life is good. So there we go. Well, don't do that. Now we're just dropping the balls. Oh well. Sudden gust of gravity for us. There's the conveyor belt model. We can use this conveyor belt to actually help us understand how transitions can occur. So let's think about what's going on. So suppose I want to go between two states. We'll call them state 1, state 2. So I start at state 1 and I end at state 2. Well, what has to be true? Well, so suppose this is state 1. Now what's going to happen is that we're going to move everything forward one time step. Now this last endpoint, which is what's scheduled to land in one beat, there might be a ball there, there might not be, but everything else, watch what they do. They shift by 1. Did you see that? They choop, shift over, choop, one step. And so what happens is, see, previously we can actually go backwards in time. Hard to do that with juggling. And say, hey, this was scheduled to land at 1, 2, 3, 4, 5. Now, where is it going to be? Well, 1, 2, 3, 4. And all of these. This was going to land at 2. Now it's going to land at 1. This was going to land at 4. Now it's going to land at 3. So what that means is it says, hey, if I have state 1 has some place where there's an occupied cell, say in the ith slot, then in the next state, which we're calling state 2, in the next state, see, time has moved down. In other words, that ball is getting closer to landing. And so it has to be that the I minus 1th slot is now going to be 1. What about this last ball, though? The ball that landed? Well, the answer is it can go anywhere. So there's no restriction. So that's why we say, look, it has to be the case that, I inherit some ones from the previous state. And the ones I inherit are the ones that are not scheduled to land right away, but are getting closer to landing. But I can also insert a new one somewhere, one somewhere, if there was a 1 in the first slot to begin with. So that's how we know where we can transition. So there's sort of a basic simple rule. What do we inherit? But we can actually go beyond just that. You see, not only do we know, can I transition from this state to that state, if we do, we know what kind of throw happened. So there's information stored in the transition. Now, what could happen? Well, see, if I'm in state 1, and the first entry is a 0, right? That means there's no ball that's landing in my next beat. So time moves on, and what happens is nothing, right? There's no ball that came in, no throw will occur, and everything just shifts down by 1. All right, fantastic, great. Okay, so that's a 0 throw. Now, if there is a 1 in the first slot, that means a ball landed. And then what? Well, now I have to say what happened to it. So let's think about what's going on. So suppose I'm in a state 1. Let's say we'll write down a state. We'll just make one up really quickly. 1, 1, 0, 0, 1, 0, 1, 1, 1. Okay. Dot, dot, dot. All right. That would be a really challenging pattern. But of course, again, we're in theory. So we can talk about it. So now let's talk about our next state. So this is state 1. And we're going to think about state 2. And so what happens is I'm just going to put in some little slots here. And because, our ball could go anywhere. And let's point out that there are some things that are inherited. So this 1, which is going to land currently at 2 beats in the future, after 1 time step, now lands 1 beat in the future. And here, similarly, this 1, 2, 3, 4, 5 beats in the future will now be at 1, 2, 3, 4 beats in the future. And this at 7 now goes to 6, and so forth and so on. So those we already know. So we say, okay, great. We have these inherited positions. And now we say, okay, what else? Well, we know that there was a throw that happened. And what we look for is we say, all right, where's the odd one out? In other words, where's something that didn't get inherited? And maybe there's a 1 there. Okay? And everything else is a 0. So using the two colors here just to emphasize what's going on. And we say, aha, some of the ones we got just because there are already balls scheduled to land, but there was one new one that wasn't coming because there was something scheduled to land. So this one right there, that is the new one that got introduced. You'll see it tries to make it sound very fancy. It says, look, there's the ith entry is 1 in the second state, but when you go to the previous state, it was a 0. Well, that just means it had to be the result of the throw. So now we say, okay, well, how many beats? 1, 2, 3, 4, 5. So this is going to correspond to a throw of 5. So that's what we can do. So now we're like, great, perfect. We can understand the transitions are going to record how the balls are landing and also going to tell us, say, hey, if you made a throw, what kind of throw did you make? Or maybe we didn't make any throw. That's fine. We can tell you that too. So the states store a tremendous amount of information, especially when we start keeping track of transitions, how things connect together. So this is good. We can learn a lot from this. So let's try an example. So here I've listed a series of states and I indicated transitions. So we start here to there, to there, to there, to there, to there, and back again. You say, all right, what is the site swap? In other words, we're like, okay, let's go back to our old juggling notation. Maybe we're like, okay, we're interested in what this would correspond to in terms of actual throwing. Because site swap is a great way to actually put things into practice. When you're juggling, you don't think about states in the back of your mind. Usually, especially at the beginning, you're thinking, oh my gosh, there's a ball! I need to do something! Woo! Hope that lands at the right time. After practice, the panic starts to subside quite a bit. Okay, so what do? Well, we do what we just did before, right? We say, all right, let's look at what gets inherited. So we can simply just say, all right, when we come here, we say, aha, these ones, past the first beat indicate, all right, great. Those are going to slide down. And then we say, all right, this is our new one. So what would that be? 1, 2, 3, 4, 5, 6, 7. Okay, so we're going to have a 7th row. So this transition here is a 7. All right, and again, we look at how things move over. We say, all right, what's new? Well, this time, it's this slot is the new slot. 1, 2, 3, 4, 5. So this transition is 5. All right, we keep going. Again, we say, all right, what slides down, and where's the new entry? There it is. 1, 2, 3, 4, 5, 6, 7. Oh, it's another 7th row. All right, well, hopefully by now you're like, oh, this isn't so bad, because it shouldn't be so bad. That's our goal. Anyways, 1, 2, 3, 4, 5, 6, 7, 8. Ooh, it's an 8th row. Okay. All right. Boom, boom, boom. And boom, boom. Right? You're like, wait a second. There's nothing new. Well, yeah. Because look at where the start is. Start is a 0. Whenever the start is a 0, it automatically means what? It means it's a 0 throw. Nothing was available to throw. So you couldn't do anything. All right, now what happens? Well, of course, it's a little bit harder to do it wrapping around, but we can say, okay, certain things line up. So that one and that one line up, and then this one matches with that one, and this one matches with that one. So what's new is actually that entry right there. And so that would be a 1, 2, 3. And there we go. So our pattern is 757803. That's our site swap. And we're done. We're done. So once we have our states, we can talk about moving from state to state. We can talk about the throws that are made. And if we have this cycle of states, we're like, look, that cycle of states corresponds to a site swap. And we've already seen in an earlier example, like, oh, if I have a site swap, construct a juggling diagram, I can talk about the cycle of states. So there's this beautiful correspondence between, cycles of states, juggling patterns, and it all fits together really nicely. Now, one thing we should note here, and if you look, you might say, oh, hey, we actually repeated a state 2 times. And this isn't the first time we've seen it. It's perfectly allowed to repeat states. And one of the things you might notice is actually when we did it, and one time we came out as a 5, and another time we came out as a 3. In other words, there were different throws that happened. And so repeating states, perfectly fine, no worries. And all right, great. So now we have a great tool which gives us more information. But can we go even further? In other words, can we get even more? It's not just hey, I can describe a little bit extra information, but can I turn it up and actually start to discover? Is this a tool for discovery? And the answer is yes, and it's really cool, but we're going to have to talk about something for just a moment. So let's switch gears for a second. So we need to talk about graphs. Now, a lot of people hear the word graph, and they're like, oh, I know about graphs. It's like, you have the graph of something like e to the x or x squared. Yeah, I've seen graphs all the time. But that's not the kind of graph we're talking about. When we talk about graphs, what we're really talking about are relationships between objects. And so there's this beautiful theory, it's called graph theory. And at its core, graph theory says, how are things connected? So what is a graph? Well, a graph consists of 2 things. One is what we call the vertices, and they're the objects. They're the things that we're interested in talking about, the connections. The second thing are what we call edges. And the edges are useful for saying, okay, which things are connected? And that's it. That's what a graph is. It's a set of objects and connections, you might say relationships, between the objects. Now, you might say, okay, that seems really broad and very general, and that's because it's really broad and very general. In fact, graph theory can model lots of different things. So it can model very specific mathematical structures. Oftentimes we have things with lots of symmetry. There's lots of beautiful graphs that you can generate out of them. But you can also model things that are more applicable. You can say, okay, well, maybe I want to model relationships or friendships, if you will. And say, okay, what if I'm trying to model friendships? What would I have? Well, you would say, okay, my vertices are, say, people, and my edges I'll connect if people are friends with each other. All right, well, fantastic. That's a beautiful way to think about it. And, of course, there's other things that you can model, things like, say, road systems, and so forth and so on. Now, there's lots of different types of graphs that you'll hear about. We're going to focus on what we call a directed graph. So what's the difference between a directed versus undirected? Well, a directed relationship says, okay, I can go one way. It's like a one-way street. So you can imagine you're in a terribly designed city where most of the roads go one way. So look, I can move from point A to point B, but not necessarily from point B to back to point A, unless there's also another edge. When we're undirected, we can say, look, if I can go from A to B, I can go from B to A. Perfectly fine. So here we see sort of some pictures of what an undirected versus a directed graph might look like. So undirected, we can put our vertices as points. And really, when we talk about graphs in this way, these are visual representations. Graphs themselves, remember, are very abstract. And so they're just, at its core, they're about sets. But I think seeing pictures helps us say, ooh, cool, pictures. So we see collections of objects, and we see some kind of ways that these objects connect to each other. So for instance, if we were talking about friends, here we see these three form what we would naturally call a triangle, and it's sort of like a set of three mutual friends. Of course, sometimes you might have things where we have loops. Well, I don't know what that means about friendship, but there can be other interpretations for graphs as well. If we come over here to directed, you see now we have arrows indicating which way can I move. So I can move from one state to another state, for instance, but not necessarily back. But, sometimes you might say, hey, look, I can go between these two vertices, because now there's edges both directions. And so, there we go. So that's the intuition. So graphs are, remember, graphs are how do objects relate to one another? How are they connected together? And if you can remember that, that's the core of graph theory. So our graph is going to be called the state graph. And you're like, okay, states, we've been talking about states. So what are our states? Well, the states are going to be the vertices. So we say, okay, so we have lots of states. Now, generally speaking, when we make this graph, we're going to have some parameters involved. One parameter is the number of balls. So that's the number of times you get a 1 in those 0, 1 patterns. And the other thing is usually there's a height restriction put in place. So we say, okay, we want to have all states with some maximum height. Now, the advantage of this, it really says, okay, we want to make it sort of very applicable. Because a lot of times when we talk about the theory, we say, okay, well, we can juggle and we can throw the balls as high as we want. If we wanted to, we can throw it up so it lands a million beats in the future. No, we can't do that. Impossible. So when we add this restriction, say, look, our states can have sort of a maximum length that really says there's a maximum height you can throw to. So this is a wonderful way to explore patterns which have a fixed height. In other words, I can't throw above some height. Now, it is possible to say, look, I don't care about height restrictions. Let it be, arbitrarily high. In which case, you have a very, very big graph. There's actually going to be infinitely many vertices. Now, one thing we should point out, it's actually very easy and quick to observe, is if we have a height restriction and we have a ball restriction, then we can put those two together and say, well, how many vertices are we going to end up with? Well, the answer is that the number of vertices that we have is going to be equal to H, choose B. Well, what's going on? Well, our states are going to be 0, 1 strings of length at most H. So there's H slots. B of those slots have to be a 1. And so I just have to pick which B of the H do I put the 1s into, and there we get the H choose B. Now, you might wonder, this is just a little side note for all you graph theory fans out there. Okay, I have H choose B vertices. Can I always get from one to another? And the answer is yes, you can. And it's a lovely little exercise to show, and we won't go through it right now. So now we have our vertices. There are states. Let's talk about our edges. So we're going to have directed edges. And the directed edges are going to connect states which can occur consecutively. Because in other words, really the key for our states is what happens from one beat to the next beat. What happens to our states? Now you notice we underline the word directed. And that's an important thing because what's going on here is that we want to talk about things which have sort of a direction involved. So why does it need to be directed? Well, you can imagine the following. Let's say here's a state, 1, 0, 1, 1, 1, 0, 0, 1. All right, and now we can transition. So I'm going to put an arrow here because this is one of our vertices. It's a state. And where does it transition to? Well, it can transition to 0, 1, 1, 1, 0, 1, 1, right? So this 1, we threw it, so it came just before the end. That's a valid transition. Now, can I go from this state to that state? And the answer is no. And it's easy to see because we don't even have to think very hard. We say, look, see that 0 right there? That 0 right there says there's only one option. See, as soon as you have a 0 in the front, you only get one option, which is to say, look, the balls are so high that at the next beat, nothing lands, which means everything just moves closer to landing. And so I have no choice. And so the only thing that can happen from this state is that it can go to 1, 1, 1, 0, 1, 1. So notice I can't go back. So that's why we're going to insist on having direction with our edges, because we aren't always guaranteed that we can go from one state and then go back to where we were. Now, sometimes we can, but when we don't know that we can, that's when we put directions into our edges. All right, so now we have our basic idea. We have our state graph. So let's take a look at a nice simple example. So here's the state graph when we have 3 balls and maximum height 5. And I know you're probably thinking, Steve, I thought you said a nice simple example. This doesn't look like that. But in some sense, this is not an unreasonable graph. Let's check a couple of things. What about the number of vertices? What did we say? Well, we said it should be H, choose B. In our case, H is 5, B is 3, so it should be 5, choose 3, which would be 10. How many states are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, 10. Good. Whew. Awesome. There's something else we can actually do. One thing we just said is, hey, if I have a 0 at the beginning, there's only one choice. So I'm forced to have a transition. So that means if we were to look at this graph and we were to pick a vertex with a 0 in the front, then the only thing that can go out, right, because that's indicating a transition to something, I can only have one thing going out. And so you'll see, for instance, here, if I'm 0, 1, 1, 1, I can only go to 1, 1, 1. Or here, if I'm 0, 0, 1, 1, 1, I can only go to 0, 1, 1, 1, and so forth and so on. All right. Well, what's something else we can do? What if you have a 1 in the front? Then how many things can go out? We can actually answer that question, right? So how can we answer that question? So if I have a 1 in the front, well, that says, look, take that, that's my ball. I have my 2 remaining balls shift down. And how many slots are left for me? There's a total of 5 slots. 2 of them are filled. So that says 3 slots remain. So my ball can go into any one of those 3 slots. So everywhere where I see a 1 at the start of a state, I should be able to connect to 3 things. And so here we go. Let's check this one. There should be 1, 2, 3 places to connect. And okay, how about here? There's 1, 2, 3 places to connect. How about this one? Well, you can see there's 1, 2, and this one actually has the ability connecting back to itself. So this is, again, a loop. Now, a couple of things you might say, Steve, what are all these numbers in red? Okay, so those are to help us read a little bit about the graph. And in particular, they're not important to the graph. They're sort of additional information. And what those are, they're telling us what are the throws that correspond to these changes in the states. So for instance, if I were to go from 1, 0, 0, 1, 1 and end up at 0, 1, 1, 1, what throw occurred? We know how to do that because if we know how states transition from one to another, we can reconstruct the throw. And that says it had to be a throw of 2. All right. Now, at this point, you might say, wow, how do we use this? And this is where things get really cool and really beautiful. What's going on here is we think it back to what we've been seeing so far. And in this session we've seen, hey, if I have a juggling pattern, I really have a sequence of states that come back to where it began. So we're going to do that in the graph. So there's something called a closed walk. And what a closed walk is, it's a sequence of states, generally we say vertices, and that start and stop at the same state. And so when we talk about sequence, we're saying this one can connect to that one, can connect to that one, and keep going until we get back to where we start. We are allowed to repeat, by the way. So what that says is we can just start and we can move around in our graph just following the arrows. And if we do that, say here we go 4, 5, 5, 0, 1. We're back to where we started, 4, 5, 5, 0, 1. Well, what does that mean? It means 4, 5, 5, 0, 1 is a juggling pattern because we can read off the throws, 4, 5, 5, 0, 1. It's a closed walk. I started and stopped at the same point. I could even do 3, 3, 4, 5, 5, 0, 1. And I can do all sorts of things. So what we see is we have this wonderful way to explore juggling patterns now. These juggling patterns are closed walks. Closed walks are juggling patterns. And so now we have this beautiful space to explore, to discover new things. And I will say that most three-ball jugglers will spend their juggling career in this diagram. Almost every pattern that three-ball jugglers learn show up somewhere here. So let's point out to some of the more famous patterns that we've already seen. So for instance, here's a very short walk, just back to itself after one step, and that's 3. So that tells us that our 3-ball cascade here, that's just that one loop. So there's one pattern, is that loop right there. How about here, 1, 5? What's that? Well, 1, 5, that's our shower, where we have 1, 5, 1, 5, 1, 5, 1, 5. All right, great. Doom, doom. You might notice, hey, there's a pattern right here. What is that? Well, 2, 4, 2, 4. Okay, what does that look like? Well, it looks like this. Whoop, where you do 2 balls in one hand, and you just hold on to the third ball in the other. So there we go. There's a pattern. How about some other ones that we've seen before? Here's a nice one, 4, 4, 1. 4, 4, 1. Do you see that? That triangle? All right, great. Well, that's a really famous pattern. And, well, it's so famous, it's a little shy. It doesn't want to be on film, I guess. But 4, 4, 1, 4, 4, 1, 4, 4, 1. Okay, great. There we go. That triangle. We just discovered 4, 4, 1 again. It was there, right there, ready to be plucked out. And, of course, you can combine things. See how we have this 3 next to the 2, 4? So we can talk about 3, 4, 2, 3, 4, 2, 3, 4, 2. What's that? Well, that actually is very simple. It looks like this. 3, 4, 2. There you go. All right. Lovely. Lovely. Can you see the baby juggling pattern? Do you remember that one? That's the pattern 5, 2, 5, 1, 2. Now, it has to be there because that involves 3 balls. All the throws have height at most 5, and it is there. So it's 5, 2, 5, 1, 2. So it's coming back and forth. Up. Sorry about that. So 5, 2, 5, 1, 2. 5, 2, 5, 1, 2. There we go. And, of course, there's, let's see, that would be 2. Okay. Here's one, 4, 4, 4, 0. There we go. Do you know what that one is? 4, 4, 4, 0. It's actually a good one if you're trying to learn to juggle 4 balls. And you might say, but wait, it only has 3 balls, so what does it look like? So what it is remember the 4, 2 that looked like this? Well, 4, 4, 4, 0 says now instead of just holding it, we're going to actually throw it. Now you might say, well, where's the 0? It's over here. So you can do So you can make a little clicking sound. And anyways, and so forth and so on. There's lots and lots of patterns. And so most of the patterns that you learn when you start out that involve 3 balls, they're somewhere in here. And of course, if you want to discover new patterns, it's pretty simple. You just say, all right, let me just put my finger a starting place. Let's say I say I want to start here. And then you just sort of move around and you record what your throws were. And you keep moving around until eventually you get back to where you started. And as you record those throws, in other words, those numbers along the edges, and you get back to where you started, guaranteed that's something that can be juggled. A successful pattern that involves 3 balls, maximum height at most 5, and life is good. Life is beautiful. So wonderful. We have a new way to explore patterns and to find patterns and to describe patterns. And we're going to see that this view of juggling actually has some really beautiful things you can do with it. And so that'll be in our next couple of sessions that we talk about.